I would, again, strongly encourage you to have out paper as we go over this warm-up question. So the question says, a 12 kilogram block is pushed from rest 2 meters with 25 newtons of force across a level frictionless platform. It slides until it collides with a 6 kilogram ball resting on the platform's edge. The block continues forward at 1 meter per second and the collision launches the ball horizontally into projectile motion. If the platform is 1.7 meters high, what is the launch speed of the ball and how far away does it land from the platform's edge? Okay, so we have just combined a bunch of different things into one question, which we could totally do on a FRQ on a test. Okay, now I'm not saying it's going to look like this one, but this is something that we could do. Okay, so let's go ahead and see if, well, hopefully you guys got some of it figured out, but let's see how you did. So if we take a look, the first thing I'm going to recommend that you do is to draw a picture. Okay, so there's a lot happening here, so it would probably help you to have a picture of what's going on. Okay, and so what's going on is there was work done on a block to get it to move, and then it moves, it slides, it hits a ball, so we have a collision, and then that ball gets launched as a projectile. Okay, that's what was described in the question. So I don't have all the numbers here, but I do have some of them. Okay, and so you can copy down my picture, you can add more stuff into it, but this is basically the scenario that was described. So if you draw it, it helps you see the different parts because there are different pieces of this scenario that you have to analyze in different ways. Obviously, like for the projectile part, you have to use projectile motion stuff, but there's also a collision. We also have to use conservation of momentum. There's also work being done to get it to move. We have to use work energy theorem. Okay, so there's a lot of different things happening here, and so you do need to identify the different parts of the scenario. Okay, and so those parts are, and I just mentioned them, but there's work done on the block to give it kinetic energy. It says that there's a force applied for a certain distance to get it to move. And so that's our work energy theorem, and we can use that to find how fast it's going after that push and before the collision. So after that work is done, how fast is it going? And then it's going to be going that speed when it hits the other object because it's said that the platform's frictionless. So there's nothing else that would be slowing it down. Okay, part B is the collision itself. Here we're going to use conservation of momentum in order to figure out what the objects do after the collision because we know that momentum is going to be conserved. So if we know how much we have beforehand, which we can figure out, then we can figure out what happens afterward. Okay, and that's the last part is afterward. That ball, it says, gets launched horizontally as a projectile. So we need to figure out from the collision how fast it's going so that we can then answer that last part of the question, which was how far away will it land. Okay, so again, this is combining 3 different units into a single scenario. So you have to be able to get all of those pieces, and so I have them kind of labeled up here. So it would help for you to kind of go through that same thought process. You don't necessarily have to write out, I have to do this, this, and this. You can, okay? If it helps you to organize it by listing it like this, for sure, absolutely do it. Okay, but you don't have to write out, I'm going to use work energy theorem and then I'm going to use conservation of momentum. You don't have to write it out, but you do have to go through the thought process. All right, so let's start with the first part of this scenario, and that's the work done on the block to give it kinetic energy. We're going to find the velocity of the block prior to the collision and, of course, after the work has been done. And so we need to write out an energy transfer equation. This block initially was at rest on this platform, and then there was a force applied to it to do work on it to give it motion. And so we know that our equation is going to look like this. The net work done on that block is going to equal the kinetic energy that it has after the work is done. So however much work was done on the block is going to help us determine how much kinetic energy it has, and of course if we know that we can figure out how fast it's going. Okay, so this is the first step, and so we know that work is force times displacement. They didn't tell us the work that was done. Instead, in the question they told us that there was a force of 25 newtons applied for 2 meters. And so we're going to multiply that 25 Newton force times that 2 meters, and we're going to set it equal to 1/2 mv squared. That's our kinetic energy equation, and we're looking for that velocity of the block. And so I have all those numbers plugged in. 1/2 times 12, that's the block's mass, times v of block squared. That's going to give us this. 50 equals 6v squared. And then, of course, we'll divide by 6. That's 8.33. And then take the square root. Okay, so I have rounded it, but I have the velocity of the block after the work is done as 2.887 meters per second. And that's how fast the block will be going until it hits the ball. Okay, so it's going to be moving at that speed because of the work done, and then there's going to be a collision, but that hasn't happened yet. Okay, so right now we're just sliding along at a speed of 2.887 meters per second. Okay, before I go any further, does anybody have a question about the first portion of this problem? Okay, because this is one, this is like energy stuff we've been doing in this unit. In fact, we actually learned the work energy theorem last semester in November or December. All right, so now that we know how fast it's going, we can focus on the collision. Okay, so the block is going to slide at that speed that we just found, and it's going to hit a ball that's at rest, and that's what it said in the question. I have that part of the question up here. Okay, and so we're going to try to find the velocity of the ball immediately after the collision. And the reason we want to do that is because one of the questions we're asked is how far away the ball lands. So we obviously need to know how fast it's going when it gets launched so that we can determine its range. Okay, so we also need to find the launch speed of the ball. That was another question. So we're going to draw the initial and final states of our collision. So when we have our collision, we have a before and after, and we've been doing this every time we deal with the collision. And so we have our block moving 2.887 meters per second, and it's going to collide with our ball that's at rest. That's before. After, we know that the block continues moving forward at 1 meter per second, and we're trying to figure out what the ball does. Okay, and again, all of that was in the question. Okay, well, actually, this speed wasn't, but this one was, the 1 meter per second. The block continues forward at 1 meter per second. This one, of course, came from part 1. Okay, so again, if we're dealing with a collision, we're going to be dealing with conservation of momentum. We know that in a collision between two objects, momentum is conserved, so that block's going to lose some of its momentum, but the ball's going to gain it. Okay, and so we know that the total initial momentum of the system equals the total final momentum of the system, and we know that momentum of each object is m times v. So we know we have m1v1 initial plus m2v2 initial equals m1v1 final plus m2v2 final. So that's what the equation we're going to use in order to substitute in here. Okay, so if I plug in my numbers, I have my block's mass of 12 multiplied by its velocity of 2.887. The initial momentum of the ball is 0. I didn't bother multiplying by the mass because 6 times 0 is just 0, so I put a 0 in there. And then that's equal to the final momentum of the block, which is 12 times 1, plus the final momentum of the ball, which is 6 times the velocity of the ball final. Okay, and so from here, again, it's just algebra. That 12 times 2.887 is 34.64 equals 12 plus 6 VF. Again, please remember, you cannot add these. This cannot become 18V. Okay, that's not a thing. Algebraically, that is not how you solve this. These are not like terms, so instead we're going to subtract 12 from both sides, and then we'll divide by the 6. Okay, so subtracting 12 from both sides gives us this, and then we'll divide by that 6, and that will give us our final velocity of 3.77 meters per second. So the ball, after the collision, is now being launched off the table because it says it's on the edge. But that's its velocity as it leaves the platform is 3.77 meters per second. Again, the first two parts of this problem are things we've been doing in this unit. Okay, so those should hopefully have been easy enough for you to figure out. But does anybody have a question about this part? Because the last part is going back a unit, okay, to projectile motion. So let's look at what happens now, because the last part of this scenario is after this ball gets hit, it's moving 3.77 meters per second. How far away does it land? And that's what the last question said. And so we got to remember projectile motion too. Okay, you know you're going to see it again. Okay, so let's go ahead and take a look at this problem. You'll notice I've already filled in my table. Whenever we deal with the projectile, as a reminder, you do have to keep your horizontal and your vertical data separate. Okay, and so I have my initial horizontal velocity as 3.77 meters per second. That's the number we just found a second ago as the velocity when it leaves the collision. So I know that's how fast it's going. It is a horizontal velocity. Vertically, it's not moving. The collision happens and it launches it horizontally. It says that in the question, so my initial vertical velocity is 0. I do know that horizontally I have no acceleration because horizontally I have no forces. And so my final horizontal velocity is also 3.77 meters per second, and my horizontal acceleration is 0. Vertically, however, I know that I have acceleration due to gravity. That's going to be negative 9.8 meters per second squared. And vertically, I know that it has to fall from the height of the platform to the ground. So it has to fall 1.7 meters because it said that the platform was 1.7 meters high. And so I filled out everything that I could into my table. Ultimately, we're trying to find range, which is going to be our horizontal displacement here. However, we cannot solve for that without first finding time. And so we're going to find the time that the ball is in the air. We're going to find that using the vertical data, and then we'll take that time and plug it in with our horizontal data. Okay, so let's look at our vertical data so we can find our time. So looking at just this side of the table, remember, don't pick from both sides. We have this equation, delta y, that's my displacement vertically, equals VIT plus 1/2 AT squared. With this formula, I can find time because I know delta y, I know A, and I know VI. So if I substitute in, I get this, negative 1.7 equals 0 plus 1/2 times negative 9.8 times t squared. That becomes this, negative 1.7 equals negative 4.9 t squared. When I divide both sides by negative 4.9, those negatives cancel, leaving me with 0.347 equals t squared. And then, of course, I need t, not t squared, so we're going to take the square root. And we get a time of 0.589 seconds. Okay, so now we have the time that it's in the air. With that, if we put that number into our table, we can now solve this. Okay, so horizontally, I now have my velocity and my time. Those are the only two variables. You'll look up there, everything else is saying the same thing. The fact that the velocity doesn't change tells me the acceleration is 0. I have a constant velocity, I have a time. And so I'm going to use this equation. I know it looks funny up here because I typed it in a line, but it's the last one of the kinematic equations on my board. It's your average velocity, VI plus VF divided by 2, times your time. So velocity times time, that's it. Okay, and so I can find my displacement by taking my velocity, 3.77 plus 3.77 divided by 2 is, of course, 3.77. That is my average velocity, times my time of 0.589. And if I multiply my velocity times my time, I get my range, and that is your answer, 2.22 meters. Are there questions about this? None of this is new. We're just taking things and putting them together. You do have a question like this in your assignment today. That's the main reason I wanted to go over it. With projectile in it. All right. So here's the answers to the warm-up. The launch speed of the ball was 3.77 meters per second. The range of the ball was 2.22 meters. All right, please make sure that you put those answers into My Open Math. And if you have any questions about this and haven't asked them, then please make sure that you ask before you leave today. Or as you're working, because as I said, you have a question that looks like that on your assignment. Your assignment for today is 906, Conservation Mixed Practice Review. It is due by 11:59 p.m. tonight because you have a quiz tomorrow. Use this opportunity to get ready for that quiz. Okay, so work through that review. It is set up so that you can answer those questions numerous times without any point penalty. So should be an easy 100. It may take you a couple tries on some of them. We'll see. Hopefully not. But it should be a 100 if you go through and you try them until you get them right. Again, make sure you get it finished by 11:59 p.m. The other thing that you need to keep in mind, your RA is due tomorrow. So if you haven't finished it yet, that is another assignment for you to be looking at. Okay, so don't forget about that as well. All right, I'm going to go ahead and let you guys get to work. If you have questions for me as you're working, please let me know.